We will start with the first talk by Ruth Jarman, who is one half of the artist duo Semiconductor. Semiconductor is UK artists Ruth Jarman and Joe Gerhardt. Over the past 25 years of collaboration, they have become known for a unique and innovative body of moving image works, sculptures, and installations which explore the material nature of our physical world and how we experience it through the lenses of science and technology. Their works bring into tangible experience that which is outside of what is humanly perceivable, confronting the viewer with information which is ordinarily outside of a human scale, both of time and space. We are very pleased to welcome Ruth and Semiconductor to get to know more about your work. So please, the floor is yours. I'll stop sharing now. Yeah. You're mute, Ruth.
There we go. Just kidding. Thanks a lot, Anna. That's great introduction. So I'm going to talk for about 25 minutes and I'm going to talk about 3 or 4 works. And that's a really great introduction. I'll skip some of the initial bit that I was going to say because then I can spend more time talking about the work. And so yes, we have this interest in the material nature of the physical world, and we've had a lot of amazing opportunities where we've been able to go into science laboratories over the years and spend time with scientists to really look at the tools and the processes and the techniques that they're developing to create an understanding of matter. And so this is really what we're interested in doing. And some of the reasons we're interested in doing that will hopefully come across as I talk about several of the works that we've made over this time. And we show our work all sorts of different places, museums and galleries, biennales, media and film festivals, science festivals, and in the forest, where we're going to start talking about the first piece of work. But we've also had lots of different collaborations with scientists all over the world. So some of them I'll be talking about today, and specifically with Matt Wilkinson, who's here. And also I'll be talking about a project that we did with the University of Dundee, and also one at CERN, the Particle Physics Laboratory in Geneva. But we've also spent time at NASA Space Sciences Labs, Mineral Sciences Laboratories, at the Smithsonian National Museum of Natural History, lots of different places all over the world. And we like to spend quite intensive time in these environments to really go beyond the way that the scientists might sort of present what they're doing. So this is a project we did in 2014. It's a sculpture that was in the Alice Holt Forest for Forestry England Forest. And so we did it in 2014, and it was a commission it was called Jerwood Open Forest. And so it was the Jerwood Foundation and Forestry England coming together to commission artworks for various spaces around the UK, various sites. And so we described this artwork as being something which considers scientific data as a representation of nature. So we're trying to explore a divide that we see exist between how science kind of describes and represents nature and how we as humans experience that. So the starting point for this project was a forest research experimental forest that was very close to where the final artwork was sited. And we worked with forest research scientist Matt Wilkinson, who has this fantastic, so you can see the forest in the top left-hand picture there, and he has this 20-foot high Flux monitoring tower in the center of the forest, which you can see this tower on the right-hand side, a big wobbly scaffold tower, which we felt that we had to climb to the top if we were going to be using the data from this tower. Then we had to make it to the top, and it was very wobbly and high, but you get to the top and you're just above the canopy of this incredible oak experimental forest. And so there's various instruments on this tower which are collecting atmospheric data, and so they're mostly looking at carbon sinking in the forest. And so they're collecting 3D wind data, temperature, carbon dioxide concentration, and water vapor concentration. And we worked closely with Matt to acquire the data that he'd been collecting, which was in this very old DOS format. So quite often when we're working with scientists, we're kind of having to navigate all these different kind of formats and find a way to work with it, to translate that. And we worked with a year's worth of data for each of the instruments. So we wanted, on the one hand, it's a kind of cycle, this yearly cycle that the scientists would be looking at to understand patterns coming out of that data. But for us also, we were thinking of it in terms of kind of it being a human time scale. So kind of we're always thinking about how we as humans exist in the kind of larger universe and the kind of rhythms and patterns and the scales that we work with as humankind. So we worked with all of these different strands of data, and we were interested in one visual technique that scientists use to plot data when it's collected cyclically in this way is like polar plots. So there's the circular diagram there with the colourful loops laid over it. And this sort of represents a year over this 360-degree period, as this example shows here. So we wanted to take these scientific methods for recording and presenting information that we collect on our environment and see what it becomes when nature is translated through this, so that it says as much about kind of how we as humans create tools and languages to understand the natural world as it does about the nature that it's studying. So we use the polar plots as the basis for developing, using the data, working with the data to create sculptural objects. And we experimented with lots of different ways of doing this. And so we wanted to work with the data. We kind of always say that we're wanting to work with it as a material, so that in this instance, we were sculpting with it and giving it three-dimensional form. So the data that we were actually working with was strings of numbers, so numerical data, and we could quite directly translate that into waveforms. So that's something you can see on the bottom left-hand side here, where we're directly translating the data, and we're always keen not to stay true to the data as much as possible, because we're interested in what it has to say, what it is doing as a material, rather than translating it into another kind of anthropomorphized language, as it were. And so we worked with the peaks and troughs of this data, and we started creating 3D forms where we would wrap the data and overlap it over each other. And we ended up with structures like the one that you can see in the middle here. This was one of the 3D forms that we made working with the data, which the sculpture was then made from. And so Cosmos is made from wood. We wanted it to feel like it was born of and belonged in the forest. And the surface is finished off by being charred. And so on the bottom left-hand image, you can see there that was a test we did. So we're taking the data that we've created from this 3D model, and then that gets CNC'd into these triangular pieces, which then all get put together. And you can see on the right-hand image here, this is us working with fabricators Millimeter, who actually made the final work and piecing it all together. And so we're interested in this process of kind of recontextualizing the data, where it becomes abstract in form and meaning and starts to take on these sculptural properties, so that they become unreadable within the context of science, but they become a physical form that we can see and touch and experience, and they become readable in a new way. So we're kind of humanizing the data in a way which offers a new perspective of the natural world that it's documenting. And I'll just say to Anna and Peter, I forgot to start my timer, so you're going to have to tell me when I'm done. Okay. And so something else I'll just quickly mention that also came out of this time of working with Matt is they were collecting these kind of visual, they're called PEN, I think it's phenomenological eye network. So there'll be a camera on the forest floor, and then one, which I'm not showing at the moment, from the canopy looking down. So one from the forest floor looking up and one from the canopy looking down, capturing these cycles, these daily cycles. So we also collected this video that they had been collecting of these kind of yearly cycles, and worked with those to create an installation called Data Projector, which is, there's more information on our website about this work. And the picture on the right is us kind of showing that work recently in an exhibition we had in Germany. I'm going to hop on to try and get through a couple of other pieces of work. So this is a piece of work called Earthworks, which we made in 2016. What you're seeing here is a 20-meter long projection, and it's a moving image work. It's an animation with surround sound. And this is where it was commissioned for, which was Sonar Festival in Barcelona in 2016. So that was the first place we've shown it, and we've shown it lots of other places since. So the work was inspired by a visit we made to a quarry in Spain, in Lleida. And you could read, we were really interested by how you could read in the face of the quarry all these layers of the landscape. And we wanted to go looking for ways that scientists try to create an understanding of landscape formation over thousands and millions of years, whatever. And so one technique that we came across that we were really interested in was called analog modeling. And we did some research around this technique, and we found this really interesting laboratory at the University of Barcelona, which was where the work was eventually going to be shown in Barcelona. And we went and visited Oriol in his analog modeling laboratory. So you can see the bottom two left images here. Here's Oriol. And it's this very interesting technique which geophysicists have been doing for a couple of 100 years now. And they'll take what we describe as like a fish tank, and they put in these flat layers of colourful sand. And then they can, by applying pressure and motion to these, they can quite accurately replicate landscape formation over thousands, hundreds of thousands of years. And so you can see in the central bottom image, you end up with all these very colourful squiggly lines, and they can quite accurately do this. And so we wanted to work with this as a visual technique to explore how we could experience landscape formation, kind of how we could experience geological timescales within our human timescale. And we knew we wanted to bring to this sound in some way, sound and the time element to that. And previously with other works, we've worked with seismic data, and we've worked with that and turning it into sound. And so we thought it would be really interesting to collect different types of land forming seismic data. And we worked, there was already an archive which we knew how to access. We've been spending time working with volcanologists and accessing volcanology seismic data. And so we knew there was an archive we could go to. And we also had lots of other contacts of various scientists who we reached out to. And we collected 4 different types of seismic data. One of them was earthquakes. One of them was volcanoes. They think it's like the magma moving around inside the volcanic chamber. One of them was glacial data. And the other one, we worked with the University of Barcelona and went to the quarry and collected seismic data as the quarry was being quarried. And so we kind of used that to represent the Anthropocene And it's interesting because it just ends up being this kind of pure noise in a way compared to the other seismic data, which is really rich. Anyway, so we took this seismic data, we created our own animated environment. So we created our own system, programmed our own system, which simulated this process of laying colours of sand. And then we took the seismic data and we used that to animate this system and gradually morph and undulate. So you can see in the bottom right hand picture, I'll play a short video of it in a second. And so not only are you seeing the data creating this landscape, but you're simultaneously hearing the seismic data because seismic data is basically a translation of waveforms. We can translate that directly into sound. And so we're not interfering with the data in any way whatsoever. So I'll just play a little documentation of that so you can get a sense. I'm going to skip those bits. So I'm just very briefly covering these artworks. I could go into a lot more detail, but I think I probably shall keep going. Okay, so this is a more recent artwork called Spectral Constellations. So it's an artwork that's made up of a series of generative animations, which are driven by the data of young potential stars. So they're made to be shown on these irregularly shaped LED mosaics. And we've worked with the spectral data. I'll talk about this a bit more in a minute, but the spectral data of 3 young stars. So there's a unique target for each of the individual screens. Each animation represents a different star, potential star system. And then we've employed this data as a physical material again, so that it generates form and motion. So we spent a couple of years working with scientists from the Planet Disk Connection Group, which is a group at the University of Dundee in Scotland, and they're exploring planet formation environments. They describe it by observing young stars and their surrounding disks of gas and dust. So they're just these big masses of gas and dust and potential little planets forming inside them. And through this research, we became interested in the methods that they're using to capture light from distant stars to try and understand these systems, the processes that it goes through via the physical layers of translation, and then also the data that's produced and what the data can reveal about how the team are applying time in their observations. So the scientists are working with data that's collected from many different ground-based observatories, but the main data that they've been working with comes from the European Southern Observatory in Chile, which is a lovely painting of in the bottom left-hand corner, where there's 2 different types of spectroscopes. So they're collecting spectroscopic data, so they're working with collecting light from these different masses, distant masses of gas and dust. And then by studying these, they can start to understand what matter is present in these bodies of gas and dust. And something that those scientists are doing that's quite unusual is that ordinarily scientists would take this information and just say, oh, okay, this is what something is made up of. But what they're doing is looking at this data over a period of time. So sometimes they're going to historical data, and sometimes they're capturing their own data, and they're trying to see that if they look at this data over time, can they start to get a sense of the shape and form and potential kind of future systems that are emerging from these balls of gas and dust. And so we were interested in working with these different strands of data that they had over time. So each one is sort of representing a different element. And again, we worked with it in this very circular way as the systems are being described. And so we created these animations which work directly from that data. And as the different elements, kind of as there's more or less of the different elements present, these rings kind of morph and shape in the animation. They kind of overlap each other. And so they create these really interesting patterns, which is something we were really interested in exploring in the work. This idea of kind of how we read the natural world around us and how we read the visual data. So as scientists, they're looking for patterns in this data. And for us, when we're looking at these images, we're trying to make sense of reading these points of light. And so we're really interested in how our brains have this kind of sense of pattern reading to create an understanding of the world around us. And so I should probably say something about why they're being shown on these irregularly shaped LEDs. When you go looking for the areas in the sky where the scientists have been looking, they're often shaped according to how the spectroscope or the telescope has been looking out, and the areas that it's told to look in, and they're normally kind of sectioned off. So we kind of wanted to use the scientific framing, so they become like these windows that are almost reminding us that we're humans on a planet kind of looking out into space. I think I have a few more minutes just to quickly talk about one more piece of work. So I'm just going to show this quick video of Halo. I think it's about 1.5 minutes long, and then I'll briefly talk about it. So that's an artwork called Halo. Let's get that image up. So it's this cylindrical installation structure, 10 meters, and that you can go inside and walk around the outside. And the data that you can see playing on the 360-degree screen is particle data collected from Atlas, one of the experiments on the Large Hadron Collider at CERN. And then, depending on where those points of light land on the screen, they trigger a hammer around the edge to play the piano wire. So you get this kind of synchronized image and sound experience. I'll just give a little bit of background to the work. So in 2015, we were artists in residence at CERN. We were there for about 4 months, and we always go looking for all the different kind of methods and tools and processes they're using to do their work, alongside just generally poking our noses in as much as we can. And we're very sort of research led when we go into these environments. So we're not going there, although we have this kind of broad interest, we're not going there with a specific idea. We always are led by kind of the research that we do when we're there. And, you know, it's an incredible place, and we were free to kind of roam around the laboratory. I think somebody said to us that, you know, you're pretty much okay to go anywhere you want to, apart from the doors that have radioactive signs on them. And then we suddenly realized we were coming out of the doors that had the radioactive signs on them. So we figured we were pretty much going everywhere. But one of the things we've tried really hard to do when we were there was to, we kept asking different people whether we could work with data from the Large Hadron Collider. And we were working with lots of people from Atlas. And so, you know, nobody kind of really wanted to be held responsible. But I've got a picture of Mark Sutton up here because, you know, when we do these projects, and always when we're working with scientific data, whether that's image-based, numerical, or point-space data, you know, we're wholly reliant on the scientist that we're working with. There needs to be a scientist who's willing to work with us and spend time with us and help us, and who hopefully gets excited about the projects that we're doing. And Mark was one of those people, and he enabled us to be able to start working with the data because he was there sort of and by our side. Should I finish talking? I think I've done
about 3 minutes left if you'd like.
3 minutes left. Oh, great, cool. So, so it was really interesting, the kind of journey that we went on trying to get this data. So we were with Mark, and we found somebody on the last day of our residency who said, yes, you can work with that data, as long as we had to sign this document that said we would not be working with the data in any way that was readable in a scientific way, which was really interesting because CERN data is notoriously complicated and difficult to process. There was absolutely no way as artists we were going to be able to do that. But just kind of culturally, I think that's really interesting as well, because I think CERN was kind of almost one of the last places to make their data publicly available for public use. So that's like a whole other conversation about accessing and archiving data. But they did that for many reasons, one of them being that it is really easy to get the analysis wrong because it's so complicated. And I think also they're continuously finding new ways to read the data. And so potentially they could be getting information in the future from the data that they might not be able to at the moment. But yeah, I'll finish up there and then we can have any questions. I feel like I've done a very kind of surface description of these works, but hopefully you get a good idea.